Advanced Algebra 2 students, welcome to your 3.1 notes. Today we're going to look at solving systems of equations. A lot of what you'll see today is review, but I don't want you to let me down. I want you to work hard, make sure you have these down. So let's do this. To solve a system of equations, well, first we need to know what it is. A system is two or more equations containing the same two or more variables. A system that contains only linear equations is a linear system, and the solution is the set of all points that satisfies both or all equations in the system. When you graph it, you'd see that solution as a point of intersection. So you have three examples here. On the left, we have our one solution situation. In the middle, we have infinitely many. Now, this is hard to see because it's basically two lines that are exactly the same, one on top of the other. And then when we have parallel lines, that's no solution. Just a little bit of terminology for you. It's down here at the bottom, but if there's at least one solution, we say that the graphs are consistent, and you can see that word here and you can see that here because there's at least one solution. If there's no solution, we say that it's inconsistent. That would be our parallel lines. Now, the only other thing is we also look at if there's one solution, we say it's independent. Infinite solutions, we would say dependent. So a little terminology, not a huge deal, but make sure you're comfortable with it. We're going to start today by looking at just simply analyzing systems, and then we'll get into actually how you solve them. So here we go. Is the ordered pair 1, 3 a solution to the given system? Well, let's see. For this to be a solution, 1, 3 has to work not just for one, but for both equations. So we're going to test both. So I'm going to do x is 1, y is 3 equals -8. So this is 1 minus 9 equals -8, and that works. Okay, so far so good. I do still need to test the second point, so I'll have 3 times 1 plus 2 times 3 equals 9, and that's what we're trying to test. That's 3 plus 6 equals 9. That is also true, so the answer here is yes. Now again, remember 1, 3 would have to work on both equations for this to be a solution, and in this case we have that, so it most definitely is. All right, on our next one, number 2, we're going to classify each system and just determine number of solutions. We want to get these in slope-intercept form. It's probably the easiest way to make that happen. So I'm going to start with the first equation here, x equals 2y plus 6. And I'm going to subtract 6 from each side, so 2y is equal to x minus 6. And then we need to divide, so y would be 1/2 x minus 3. All right, similar process with this equation. I'm going to subtract 3x from both sides. And I'm doing this again because I'm trying to get into slope-intercept form. Then I need to divide by -6, and that's a y, not an x right there. Sorry about that, -6y. Okay, and I divide by -6, and I get y equals 1/2 x and minus 3. All right, so what we have going on here is that the two lines have the same equation. So what we would say then, of course, is that there are infinite number of solutions, and I'm just going to write infinite solutions. It doesn't mean every place works, but any place along the line works. And we would say that it's consistent. Remember the terminology. You can look back one slide and see it, but it's also dependent. Dependent. There's an N in there. All right. And again, if you don't have that terminology, just look back one slide and you'll find it there. All right, let's look at the second one here. 4x plus y equals 1. So I'm just going to subtract 4x. That was pretty quick. -4x plus 1. And then for this equation, we can just subtract 1. So y equals -4x minus 1. Okay, those, at first glance, you might have thought they were the same line, but when you look at it, you realize the y-intercept is actually different. The slope is the same. We're talking parallel lines here. And so if we have parallel lines, there's no solution. And another name for that would be to say that the two lines, the system, rather, is inconsistent. As we move forward now, what we're looking at is ways we can solve systems. And so we basically have three ways we're going to focus on: graphing, and then we'll also look at substitution and elimination. But first we'll look at graphing. This slide here, you have an example. You guys can read it, but basically it's just two lines. One was given to us in point slope form, one in slope intercept, and they're graphed here, and you can see the intersection is the point -1, 1. So that would be the solution to the system. It would be the intersection point. There are lots of ways you can explain that. But in the end, x equals -1 and y equals 1 is the solution to this system. So let's try one. Now, I will point this out as we get further into this. We won't do a whole lot of graph by hand to find solutions. We'll use our calculators to do most of this work. All right, so what I'm going to do is graph this first line by intercepts method. Since it is in standard form, that usually is a much simpler way to graph things. And as long as I'm careful, I can get a nice, accurate graph. Have my x and y intercepts taken care of, and I'm going to extend that line a bit so we can kind of see where it goes. All right, we have another line to graph. Y equals 1/3 x plus 1, so I'm going to go up. I'm going to go to 0, 1 for the y-intercept. Then I'm going to apply that slope. Up 1, right 1, 2, 3. Isn't that convenient? Up 1, right 1, 2, 3. And really, I don't need more points. I really only need 2 points. But I went ahead and went with 1 extra. Oh, I got my line off. We can fix that though. All right, that's better. And you can see right there, we have a nice, beautiful intersection at the ordered pair 3, comma 2. So that is the solution. That means if we plug in 3 for x and 2 for y, it will solve both equations. Our second method for solving systems is the substitution method. We've actually done a lot of substitutions in here. Essentially every time we deal with function notation, we're doing substitutions. So you're kind of used to doing some of this. But when it comes to systems, what we have to do, our method is to solve for one variable. Now here's the system I'm going to use as the example. You can see it here, and nicely it's already set up where y equals 2x plus 3. I'm going to let you guys follow through the algebra steps, but essentially I just rewrote the first equation, and instead of writing y, I wrote 2x plus 3, which is just from that second equation. And then it's a matter of using the distributive property, combining like terms, dividing, and then once you divide, you plug in the value to, you can choose either equation. It doesn't matter as long as you do the first part right, the second part should follow. And then we get our y value. And you can see here the ordered pair -1/3, 7/3 is the solution. Again, we could find that other methods, but if we graphed it, that would be the intersection. But this one we're going to use substitution. All right, we're going to do the same thing here. We're going to use substitution to solve these systems. So when I look at A, I have to pick what variable do I want to solve for. And to me, the easiest is this one right here, x. And the reason is it's just a 1x already. So I can make x equal -2y plus 4. Then I can take that value for x and substitute it into the other equation. So 3x minus 4y equals 7. Again, instead of writing x, I wrote -2y plus 4. All right, little distribution, so -6y plus 12 minus 4y is equal to 7. We'll combine like terms. That's going to give me a -10y. I'm going to subtract 12 from both sides, so I'll have -5. So y then is 1/2. And then at this point, I just need to plug that value for y in. I'll use the first equation, but you could use either one. It shouldn't matter. So 2y, so 2 times 1/2 plus x is equal to 4. This is 1. If I subtract 1, I get x equal to 3. And we like to write our solution to systems problems as an ordered pair, and that's what it looks like, 3 comma 1/2. All right, on part B, same kind of deal. You could solve for any variable you want. The one I want to solve for is on this second equation. There's kind of a theme here. You want to do things with as easy a pathway as possible, not out of laziness, but why complicate things if they don't need to be complicated? So what I'm doing now is I'm plugging in that value for x into the first equation, and we'll have negative 6y plus 6 plus 5y equals negative 5. This is the time where we would combine like terms, so I'd have negative y. I can subtract 6 and I get negative 11, and some quick division by negative 1 gives me y equal to 11. Now again, we just need to take that value and plug it in, so we'll have x plus 3 times 11. I'm using the second equation, by the way. If you use the first, that's totally fine. So x plus 33 is equal to 3. So x is equal to negative 30, and that gives us an ordered pair of negative 30 and 11. The final method we're going to look at today is elimination. When it comes to algebraic methods, this is the one that we probably tend to use the most. It's not better, it's just sometimes simpler or more direct. We tend to prefer it. So elimination is a really important method. You can follow the work here, but essentially what I'm doing is I need to eliminate a variable. When I looked at these two equations, to me the easiest thing to do was to get rid of the x's by multiplying the second equation, all the terms, by negative 2. So that gave me 4x minus 5y equals negative 2, no change there. And then negative 4x minus 8y equals negative 24 is this equation times negative 2. And you can see, now the whole point of this, it's the reason we did that is because of this right here. Those terms will cancel each other out, and all we're left with then is one variable. We like equations that have one variable because we know how to solve those. So we had negative 13y equals negative 26, and you can see the answer. And then we have to use one step of substitution to plug it back in, and we can find our final result. All right, let's do the same process here. We're going to use method of elimination. And when I look at this, I see that the x's are probably going to be the easiest one to get rid of. So I'm going to multiply that equation by negative 2. So I'm going to have negative 6x plus 14y equals negative 20. That gives me 6y equal to negative 12. One step of division, and I get y equals negative 2. We can choose either equation to plug that into. I'll go with the first. I don't think it really matters too much. They're not going to be much different in terms of which one's easier or more complicated. So this is 3x, basically plus 14 equals 10. So 3x would be negative 4. That means x is equal to negative 4/3. But what we're looking for is an ordered pair solution, and we have that at negative 4/3 and negative 2. Now this is our last problem we're going to look at on B. I'm using elimination again, although, hey, real quick, that's a y right there. It just looks like an x. Apparently there was a typo by someone. Maybe it was me, maybe someone else. We'll never know. But anyway, when I look at this, I know that's supposed to be a y. I'm going to multiply the second equation by 2. Now first, I'm going to rewrite the first equation, negative 8x plus 6y equals 5. Now I'm writing the second one, 8x minus 6y equals negative 30. What is going on here? That's 0. That's 0. 0 equals negative 25. What's happening here? Well, 0 is not equal to negative 25, is it? So that's a no solution situation. If you go back earlier in the notes, you'll see we ran into no solutions. That's parallel lines is what that is. So you could say they're inconsistent, but the system's inconsistent, but I think no solution's a fair answer to mark down there. I should also point out, if you ever end up with something like 12 equals 12 or 0 equals 0, that means you have the same line. So that's your infinite solution situation where you're consistent and dependent. Hey folks, I hope this makes sense to you. I hope it brings back some great memories of the olden days when you solved systems effectively, and we'll get right back to those. So come to class, ready to work. Have a lovely day.